The big thing is our upcoming test, which will be held not next Tuesday, but a week from Tuesday. So still have a little bit of time before we get there. So I have set up, first of all, a review guide. So the midterm, March 9th, going to be online on Canvas. Most likely using the Respondus Lockdown browser, which I understand many of you may not like to use, but it does prevent cheating. Just to, I did have no cheating when I used the Respondus Lockdown browser in CS140 last spring for the midterm, but then for the final, I decided, no, I'll just trust everyone, but I ended up with a bunch of cheating. And so basically the way I view it is the Respondus Lockdown browser protects you. It assures, well, it protects you from having other people cheat, and it ensures for me that everyone is presenting their own work and not someone else's work. I know it's an inconvenience. I apologize for that, but I just don't see any other good way to ensure that it's a fair exam where you're not getting outside assistance. Now, I know that some of you have older computers that don't have a camera, and the Respondus Lockdown browser wants you to have a camera. However, there is a way for me to give you permission to use the browser without a camera. So if you have a laptop or a computer that does not have a camera, please let me know before the exam. Okay, that's really important. And the second thing is, if you don't, then what I did that worked well the other time was I set up a separate Zoom session and had people log into the Zoom session via their smartphones, which pretty much all of you have. And with the smartphone, you're able to ask questions in the Zoom session, because with the Respondus Lockdown browser doesn't give you the opportunity to ask questions, which is unfortunate. But if you have a separate Zoom session that you access using your smartphone, then you can ask questions. Also, for those of you who don't have a camera on your computer, I'm assuming that most of you will still have a smartphone that has a camera, so I can have you set up the smartphone in a way that shows me the camera. So basically, you'll log into the Zoom session and you will show video. So I'm seeing a couple of hands raised. Let me just get through this and I'll take questions once I'm through this. The other thing I have not yet decided about is whether I may need to have you upload a drawing or not. That would probably come with the inheritance hierarchy, where I might need a drawing. And someone made an excellent suggestion. They said that, I think it was in their chemistry class, that as soon as the exam ended, a link opened on Canvas that allowed you like a 10-minute grace period, a 10-minute period where you can upload the file to Canvas. So I'm considering using that technique if I need to allow for uploads. Okay, so that covers that. Any questions thus far? Just speak up if you have a question.
Oh, I have a question. Is there a good, as of right now, I don't think you can, I'm running completely just Linux or Ubuntu, and there's no good way for.
No, you're right.
Should I just try to dual boot Windows for the time being, or is there like a better way to do that?
No, there's not. Unfortunately, that's the one big bugaboo, is it has to be Windows or Mac. is there a way for you to get a Windows? If I tell you what, we'll take it offline, okay? Send me some email. Let me know if it's how hard it is for you. If like sometimes you can dual boot either Windows or Linux, and that's fairly easy. If you can't, let's just do some email exchange and see if we can't figure something out, okay?
Yeah, I've actually had to do that for another class where I just dual booted, so I'll probably just have to reinstall Windows and do that. It's all good.
Okay, sounds good. I apologize for that. I wish they would come up with the Unix version too, but I guess they figure it's just not worth it. Other questions? Okay. So you can see here that I have developed a review guide. So if you click, this is just on the main course page. If you click on review guide, it takes you to what you're responsible for. So you'll be responsible for all the material up through widgets and message dialogue. So we have 3 lectures left before the exam. Today on exception handling. Then next week we start graphical user interfaces. And all I would ask you on the graphical user interface exam is questions similar to what I will ask you on the quizzes for those 2 days. So if you're wondering, how do I study for that portion of the exam? Basically, the 2 quizzes that I give next week are exactly the type of questions and material I'd hold you responsible for on the midterm. As for the rest of the material, by the time you get to the midterm, you will have completed a homework assignment on it and have had the opportunity to see the solutions. So you will be responsible for writing programs involving the rest of the material up through exception handling. I will not expect you to be able to write a Java program involving a GUI for the midterm. At any rate, if you just go through, this is it. I'm not going to go through it now, but this gives you a nice review of pretty much everything that I consider important for the exam. And then I went and posted one sample exam and its solutions. And I only give you one sample exam because I found that if I give multiple sample exams, all that students do is study the sample exams, and then I get complaints. Well, you gave me all these sample exams. I thought that that was all you would ask. And of course, I never do that. I always come up with new problems, new styles. So I try to give you one exam. It shows you kind of what my style is, but I expect you to know all the material that's in that review guide. And that's why I don't give you multiple exams. This exam that I'm planning is probably going to be more programming oriented, which is what the exam you see here was. So it had a lot of fill in the blank, which I'm not so sure I'm going to use this time. Then a few multiple choice, but mostly it had some programming questions on it. It had inheritance, where you developed an inheritance hierarchy, and it had a question where you just wrote a general Java program, and I think question 4 had you write a template class. Yes. So there were 3 questions that required a bit of code, and I think that that is how this exam is going to be more heavily weighted, is toward having you write some code that shows me you know how to write a Java program, you know how to use exception handling, you know how to write Java generics. What I will limit the code writing to is Java. So I won't make you write C or C++ code. I will expect you to be able to answer essay questions about C or C++ material that we've covered. I'll expect you to be able to read C or C++ code. And I'll expect you to be able to answer matching or multiple choice or multiple answer questions with C or C++ code. But I will not require you to write C or C++ code. I will only require you to write Java code. Okay. So I think that pretty much covers what I have so far for the exam. Any questions about that? Any questions at all? Okay. Then the last thing is I did rejigger the homework. So I combined what used to be homeworks 5 and 6 and reduced it to the size of just one homework assignment and extended the deadline by 3 days. So homework 5 is now due a week, essentially a week from tomorrow. So essentially on a Friday evening. No late submission, so I can immediately make the solutions available so that you have those solutions to study over the weekend. And you'll notice that gives you Saturday, Sunday, Monday, where you don't have to worry about homework at all, and you can simply study for the exam. And then the next homework assignment, which covers GUI, is not due until essentially 2 weeks after the exam. So you kind of, that was designed, rejiggering the homework was designed to give you a breather so that you're not trying to both finish homework and study for the exam at the same time. Okay. But it does mean also no late submissions for homework 5. Okay. So with all the preliminaries out of the way, we will move on to exception handling. So to give you a quick kind of where we have been and where we're going, for the past several weeks, we've been looking at what I would call advanced features of programming languages. So we looked at inheritance, we looked at module mechanisms, we looked at how you can create generic methods and functions. And today we'll look at the last of those advanced features, which is exception handling. So those are features where I was kind of comparing and contrasting how it's done in Java and C++ and C. From here, the rest of the course, we move into different styles of programming. So we'll start with 2.5 weeks on event-based programming, which is also graphical user interfaces. So those are interchangeable terms. Then we'll spend a couple weeks on Python, a scripting language, a couple weeks on concurrency, and finally a couple weeks on functional languages. So the kind of final, we're 1/3 of the way through the course now. The remaining 2/3 of the course is kind of more on different types of programming styles or languages. So that is where we're going. As I said, today we finish up with the last of the advanced features, which is exception handling. So let's get to it. So an exception is an unusual event. It's not necessarily an error event. For example, end of file raises an exception, but is not an error event. So it's simply an unusual condition that we need to handle. And it may be generated by either the hardware or the software. So for example, a segfault is a hardware exception. A end of file is generally also a hardware detected issue. Say a downcast to an invalid object would be something caught by the software. It would be a software exception. Out of memory error would probably be a software exception. So then we have the notion of an exception handler, which is a code fragment that processes an exception. And after the exception handler finishes processing the exception, either we may continue with program execution or we may terminate it by ending the program. So C, the original kind of language, did not have very good exception handling capabilities. So if you are in C, its exception handling capabilities are essentially return a status flag, so for example, if you do A to I, then it returns either an integer or 0 if the conversion failed. And we all know what the problem, or hopefully know what the problem with A to I is, which is, what if the string it was trying to convert was 0? In that case, the conversion succeeded, but it looks like it was a failure because you got 0 back. So the problem with returning a status code is it may be ambiguous as to whether it is actually a correct result or not. So then you will often have to have two variables, one which is the status code and one which is the result. But because you're only allowed one return value, you have to pass the other parameter essentially by reference in that case. So it creates issues. So at any rate, you can return a status flag. 2, you can pass exception or error exception handling functions as arguments. And if there is an exception, then the program that, or the function that has been called, can call the appropriate exception handling function. But the problem is, if there are multiple exceptions, you can quickly get a proliferation of these exception handling functions. So that's not particularly helpful either. The last thing you have in, actually not the last thing, another thing you can use is something called set jump, long jump. And what that allows you to do is essentially jump back to the calling function. Okay, popping all stack frames, all intermediate stack frames. And return an error code. And the fourth way is something called signal handling, where you give a function pointer. So you notify the OS that you want to handle a function called when a specific hardware signal is received. So the first three all involve software exceptions. So these three all are software generated. And the fourth one deals with hardware generated. So I'm going to give you a little more detail on 3 and 4. So here's how you use set jump and long jump, at least kind of a quick overview. So you call set jump and you give it a pointer to a piece of memory. We're not going to worry about how big that memory needs to be. In fact, what I believe happens is it's a pointer to a pointer, and the set jump command actually allocates a memory block of the requisite size and then returns a pointer or places a pointer in buffer to it. So I think a buffer is actually something like a void double star. So the first time set jump is called, it returns 0. And then when you, and it saves the current program counter, the stack pointer, the frame pointer, all the registers, and it stores it in that memory block that it allocates. So it basically stores the current program state into that buffer or into that memory. Then it returns 0. So you now have this idiom of saying if not result. So the first time set jump is called, it returns 0. So it's guaranteed that the true portion executes. So you execute whatever protected code you want to execute. That's code that you think may cause the error. And at some point, deep down, several functions deep, you may find an error. And at that point, you would call long jump, passing it the buffer. So you need to pass this buffer pointer to successive functions. And you give an error code, which is an integer that you want returned. What set jump or long jump does is it now uses this buffer to restore the register contents, the frame pointer, the stack pointer, and the program counter to what it was when this original set jump command was called. And so you end up coming right back to this statement here, but now error code is what is assigned to result. So now that as long as you return non-zero, you will come down into this else block where you will do your error handling. Okay, so it does give you a nice way to unwind the stack and to effectively jump back to, say, main if you want, or to a high-level function without having to deal with passing a status code up the stack through multiple stack frames to get back to the original call. So for example, if we're let's say we have main, which called A, which called B, which called C, which called D, it could be a pain in the neck to have to pass a status flag all the way back up the call stack. It's a lot easier if you can just long jump all the way back to main. But there's an issue here that's subtle, but it comes up, which is that you lose when long jump executes. One, you lose the contents of any variables temporarily stored in registers. That are on the stack. So what compilers typically do, when let's say in B, you have a reference parameter, or that is something like x equals 10. And it's a reference parameter. So back here in main, you really want it, maybe y is associated with this x. And you've assigned 10 to x in B. But what the compiler often does is it doesn't immediately store 10 into x. Instead, it stores 10 in a temporary register like R2. And only when the function exits does it actually flush the register contents back out to memory. And it does that because register accesses are much faster than memory accesses by several instruction cycles faster. So when B calls C and then C calls D, 10 has not yet been flushed back into X and hence back into this Y. So let's say Y was 8 when it was assigned a value in main. Now you call long jump, and unfortunately, this X equals 10, which should have been committed to Y, thus changing it to 10, the commit never happens. And instead, Y remains as 8. So that's what I mean by you lose the contents of any variables temporarily stored in registers that are on the stack. The second issue is you lose pointers to heap allocated memory. So let's say in C, you had done a malloc where you had said something like A and equals malloc something. And at the end of C, you had a delete A. But in between, you had a call to D. So the problem is, again, with long jump, it discards the contents of DCB without executing any of the so-called destruction code, and hence you lose this pointer to this malloc memory, and it becomes a memory leak. So that's the second issue with long jump, is you lose your pointers to heap allocated memory, which potentially creates memory leaks. So there is a solution to one. The solution to problem one is to declare variables as volatile with the volatile keyword. So you would say, for example, volatile int y. And you'd also have to do it up here with volatile x. And what that does is it's a directive to the C compiler that says you cannot leave a value in the register when it changes without also writing it back out to memory. So anytime you do an assignment, the volatile declaration says you have to write it back out to memory. What it also says is you can't trust what's in the register, so anything else that's relying on it is also going to have to read it from memory. So as soon as you declare something as volatile, you slow down your program because you no longer can treat it as a register variable. Essentially, all reads and all writes now must come from memory and to memory. So volatile forces any assignment to be written to memory. It also essentially forces any read to come from memory as opposed to from a register. So it slows down your program. And not only do you pay a price in terms of the additional instruction cycles to go to memory as opposed to a register, but modern processors very carefully schedule the instruction pipeline. So you're also disrupting the instruction pipeline when you declare something as volatile. So it's a solution, but it's not a particularly great solution. Okay, so at any rate, that's the issue with set jump and long jump. Okay, and then finally, like I said, in C, you can define a signal handler, and the actual function is called signal that you call to let the operating system know you want to have your exception handler called when this particular hardware signal occurs. So for example, here I'm saying that when the segfault signal is received, I want my sig handler function called, and this is my sig handler function. Now the problem with this, which is that once you're done with the exception handler, and if it terminates normally as the one here does, all it does is print the fact that I receive a segfault, it immediately tries to re-execute the instruction that raised the original signal. Well, if you haven't fixed the problem, and in this case, I did not fix the problem, all I did was print out a message without fixing whatever called the segfault, I'm just going to end up in an infinite loop, in effect, or infinite recursion, where I generate the signal, my exception handler prints this message, receive sig. Now it exits, the original instruction that caused the seg v signal to be generated gets executed again. I did nothing to fix the problem, so the signal is re-raised. My sig handler is again called. You can see what's happening. I'm just in an infinite series of handler calls. So in practice, we do not write exception handlers for hardware generated signals. This mechanism was provided for the people who actually write the operating system, who write the kernel. So while this exists, and you probably learn about it in 360, or if not, perhaps in 361, you don't use this at the application programmer level. This is really a tool that is used by kernel programmers, people who are writing system software, not application software. So I want you to be aware of the fact that you have the ability to handle a hardware generated signal in C and in C++, but unless you're writing system software, which you probably aren't, you should not use it. Okay, so questions about C's exception handling capabilities. Anyone have a question about that? We good? Okay. So here's a big problem with the C way of handling it. Any of the three ways, whether it's an error code or a status code that gets returned, whether it is a exception handling function, or whether it is set jump long jump. What happens is you generally have a lot of if statements that are detecting error conditions. So for example, you say A equals some cast like char star, and you malloc. And then the first thing you're supposed to do is say if A equals 0, some error handling. Okay, now let's say this was supposed to be an array, and the next thing we want to do is say A of I equals string dupe something. Well, the first thing we might do is say if I is less than 0 or I is greater than size, some error handling. So the problem with C-style error handling is that the code gets cluttered with error checking code. And it can become hard to follow this logic. I'll call it the main logic, which is what would happen if it executed without any errors. So in more modern In more modern languages, the goal has been to separate your normal execution from your error handling code. So in modern languages, try to separate normal code from error handling code. So each is, they try to put them in separate parts of the program. And both C++, basically all modern languages take the same approach that was introduced in C++. So we're going to spend much of our time talking about C++. Java adopted almost the same mechanism with just a few tweaks. And modern scripting languages also use typically the same exception handling capability or mechanism that C++ introduced, also with a few tweaks. So the first advantage is the code is less cluttered. The second thing that they wanted the user have to do is they want to force programmers to explicitly indicate how they plan to handle various exceptions. So for example, what if you get an end of file condition? It gets raised. They want you to explicitly consider, how do I handle an end of file condition? Or if I can't open a file for some reason, I gave a bad name, I don't have permission to open it, what do I intend to do in that situation? So rather than what you could do in C, you could just open a file. In C, you could just say something like fp equals something like fopen. And let's say it failed. And then you go ahead and you try to do something with it, like a read. And it'll just core dump because fp is undefined if there was an error. So what modern languages try to do is say, no, 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 you can't, we're not going to let you do that. If an exception happens when you do that open, we're going to force you to tell the compiler how you plan to handle that exception. Now, you can either write a block of code, an exception handler to deal with it, or you can say, I'm punting, I'm throwing this to the calling method, and I'll let the calling method deal with it. And you can actually send that all the way up and out of main, in which case the program will terminate, because in that case you're saying, I don't want to handle it, but at least you're then explicitly saying, nope, I'm not handling it, let the program exit. So that is the second thing that they're aiming for. So in C++, what they introduced was this try mechanism. So in the try block, you put the normal code. So it's the code that might raise the exception, but oftentimes you don't bother to do any error checking. Like in Java, you don't check the indices for your arrays. If a index is out of bounds, an exception will get thrown, you can deal with it. So you just execute as though nothing is going to happen. Can you still hear me? I just got internet is unstable.
Yes, just fine.
Okay, good. Okay, so we put in the try block anything That's just normal processing. And then our exception handlers go into the catch blocks. So this is where our error handlers are in the catches. And these formal parameters are basically exception objects that describe the type of exception. Now in C++, they're also allowed to be primitive types like ints, like integer error codes, although that's kind of frowned upon. But you are allowed to pass primitive types like char stars or ints. Better is if you pass exception objects, which we will get to. And then inside the catch, you have handlers that handle whatever that exception might be. And this ... in this case is actual C++ syntax. And it means catch any exception that has not been caught by any of the previous exceptions. So when an exception is raised, C++ goes through these catch blocks in sequence and tries to match the exception with the appropriate exception parameter. The first one that matches, it executes that code. It doesn't execute any of the remaining handlers, even if they are capable of handling the exception. Okay, so we'll see that in a moment, what that means. When I have handled an exception, if I don't return and I don't exit the program, then execution picks up after the try statement. It does not go back to where, it doesn't go back to where the exception occurred in the try statement. It starts executing with the statement after the try statement right here. Okay. So for example, in the try, I might have char or string star name equals new string. And you'll notice that in C++, you never check to see whether the new command returns a block of memory or whether it failed. And the reason you don't do that is if new fails, it throws an exception that can be caught. That's why you never in C++ see people checking to see whether the new command succeeded and actually allocated a string to name. It's because if it fails, an exception will be thrown. So then I could catch it with one of these catch statements and do whatever processing I needed to do. In this case, because I'm probably out of memory, I probably would print something about the fact that I'm out of memory and exit the program. Okay. So the and you're allowed to ignore the formal parameter if you're not going to use it. So you get one formal parameter, and if you don't want to use that formal parameter, you're allowed to not provide a variable name with it. Okay. So a couple things there is a gotcha that you need to be aware of. Whoops. So this is a common gotcha. Try int index cn into index, say ace of index equals 20, catch, let's say it's array index out of bounds. Pretend I had such a exception defined, and say what I did. Notice I don't have a parameter there because I don't care actually what it is. And I just try to say cout index. This gets me a compiler error. And the reason I get a compiler error is because, believe it or not, index is now undefined. Hey, you're thinking, wait a minute, I defined it in the try block. What do you mean it's undefined? C++ makes this argument. You exited the scope of the try block already. Therefore, when you exited the scope of the try block, index became out of scope and undefined. You now are in a separate exception handling piece of code, but because the try block is exited and out of scope, you cannot access index anymore. So the solution's pretty easy. You lift the declaration out of the try block, but I just want you to be aware that's a gotcha that you don't want to have get you. Okay, so you wouldn't put your you wouldn't put the index there, you'd move it outside the try block. Okay. So let's actually kind of show you an example. I think it would help at this point to actually see an example of some code involving tries, and then we'll move back. So here is an example where what I want to do is write an array that can check in C++ that does bounds checking. So if you try to use a negative index or an index beyond the size of the array, it will throw an exception. If you try to create a negative sized array, it will throw an exception. So the way I do it is I start by defining this class array exception, because as I said, it's normally better to create classes for your exception objects. And in this case, I'm creating a virtual function called response that can be called to handle the response to the exception if I want it. So I could actually put my error handling code in there if I wanted, although that probably would not be a good idea. You normally want to leave that to the specific catch block that catches it. But maybe you want to provide a default error handling. You could do it with this response function. So now I'm going to create some error conditions that are specific, more specific. So the first one is an array size exception. And that will be thrown if the program tries to create a negative sized array. So I'm going to pass to it the size variable. And there's a short constructor for creating it. And my response is to be printing that the size of the array was negative and to print out the size. So you may think that the ability to only pass one parameter to a catch block is restrictive, and it is, but you can always create a class. That class can have as many instance variables as you want, so you can actually pass multiple pieces of information to the catch block as long as you embed those pieces of information in your exception object, which is what I did here. I embedded the size, which was negative, into the exception object. Then the next one I create is my array out of bounds exception. And in this case, I want to know both the index that caused the error, but I also may want to be able to print out the size of the array. So in this case, I'm passing in two pieces of information to the constructor, the integer index and the integer size. And in this case, I defined a response that does nothing. So in this case, it says there is no default response when there's an out of bounds exception. I'm just going to leave it up to the catch clause to determine what it wants to do. So now I've defined my two specific exceptions that I will catch. One, that I will catch any attempt to create a negative sized array. Two, I will detect any out of bounds indices. So now I'm going to declare my class, which I call safe array. And it's going to be a array of integers. So you can see that I create an array, and you'll notice you're allowed to use default values for parameters in constructors. So that's what I'm doing there, is if they do not give me a value for size, I will assume it's 10. And you see that I do a check. If size is less than or equal to 0, then I throw an array size exception. Notice I don't throw new. We will get to that, but it's always a bad idea to throw a object that is allocated off the heap. You want to throw one that is allocated off the stack. So then I create my new array and initialize the values to 0. In my set function, you notice I do a range check before I assign the value. And in get, I also do a range check. You can see range check is a protected function that checks to ensure that the index is in range. And if not, it again throws a stack allocated out of bounds exception. And you'll notice here, I actually catch it and I print an error message, and then this is called a rethrow. So not only am I handling the exception, but I'm saying my response to this exception is not complete. I also want to let the calling function know about the problem. So I am rethrowing the exception up to the calling program. Here, I never caught the exception. So it is, if I don't catch it, I automatically exit the procedure at this point, and the exception is thrown to the calling function, and nothing is executed after it. So it's like a return statement. Throw is like a return statement if that exception is not caught. Here it was caught. And notice, in order to catch it, you have to have a try. You can catch has to be paired with a try. So you can always throw something. You don't need to be within a try statement in order to do a throw. If you're not inside a try statement, then the exception will be thrown out of the function and up to the calling function. If you are inside a try block, then it will first check the catch statements to see if any of those catch statements can handle the exception. If the answer is yes, then the code in that catch block is executed. And once it's finished, execution resumes after the catch. So in this case, if I had not rethrown, which I did the rethrow, but if I'd not done the rethrow, then execution would pick up after the try block, which would mean that range check would have exited because there is no next statement. And I would have returned and actually executed the statement after range check. Obviously, that's not appropriate here because I did nothing to correct the problem. So instead, I did a rethrow, which throws the exception object up to the calling function. Now, the other thing to note is I'm using a ampersand E here. What that means I'm passing the object by reference, and it allows me to modify that object. And now when I do the rethrow, any modifications I make to the object will be reflected when I rethrow. If I omit this ampersand, then when I rethrow, I will throw a copy of the original object. It will not reflect any changes I made in the catch body. So it is always good or best to catch by reference rather than by value, because it ensures that any changes I make will be reflected when I rethrow the object. I'm sorry. Yes, I want, because otherwise I'll be rethrowing a copy of the original object. Okay, so then here's my main program involving my safe array. So I create a new safe array with 100. I do a set 310, which works, and a get with -1, which won't. And you'll notice I do a number of catches after the try statement. Here's the bad ALEC. This comes out of the STD, the standard template library. It's the exception that is thrown by new when there's not enough memory. So this is catching a exception thrown by new in case I was unable to allocate the array. Then this catches my out of bounds exception. And you can see that is, will catch this -1 and print that it's out of range. Then I just ran through a loop from -2 up to 100 and did some set statements to show you that it would keep executing even after I catch it. So here, my first set is going to try to set -2, the index -2 to -2, and that's going to cause an out of bounds exception, which will print that the index is out of range. And then it will start executing again at the end of the try statement, which will bring us back to the beginning of the loop. So we will now increment I to be -1, and again we'll get an exception. So notice here, index -2 is out of range, must be between 0 and 100. And by the way, up here, this out of bounds exception, when it's originally called, notice it says caught it. So that's what happens when I try to set -2. It first says caught it, and then it threw it up to here. I caught it here, and I am printing -2 is out of range. Now I come out of the try statement, I come back up to the top of the loop, I get set to -1, and again, that's out of range. So I end up printing out the error message handling it. Now I gets incremented to 0, that's okay. It gets incremented up to 50. At 50, I tried to create a negative sized array. That is going to trigger an array size exception. And you'll notice there's no array size exception in my catch list, but there is a superclass of array size exceptions. So this catch statement catches the array size exception because it's a superclass. So a supertype will always catch a subtype. So in this case, this catch clause executes, and it executes the response method. You'll notice that for a array size exception, the response method prints the error message, the array size of blah is negative. So down here, it prints error. The array size of -10 is negative, and it comes out of the catch. The try picks up execution after the try, which brings us back to the top of the loop. We keep incrementing I, and eventually I reaches 100. Now the size of the array is 100, so the indices only go from 0 to 99. So this creates our final index out of range because it must be between 0 and 100, really between 0 and 99. Okay, so questions about how this code executes. Okay, no questions? In that case, here are some of the nuances of try and catch. So the first thing is that what catches something, if you have something of type T in your parameter list, then it will catch any argument that is of type T. I'm sorry, if you throw something of type T, then it will be caught by anything of type T or const T or a reference to T or a reference to that T. And in addition, it will be caught by any supertype of T. Okay, so here, another example, class exception, class stack exception. I should have class stack exception colon public. So I meant to have, I need to fix this. This should be public exception so that it is a subclass of exception. And in that case, all of these catch statements you see here will catch this thrown stack exception. So I'll fix that. What will not catch it is a pointer. This is not. So I am throwing a stack allocated object up here. That is stack allocated. I cannot catch a stack allocated object with a parameter that expects a heap allocated object. So when I say exception star E, I'm saying I'm expecting a heap allocated object here, and that will not catch this stack exception. So those do not match. Okay, so that's very important. Another thing that is very important is considered to be bad form to throw a heap allocated object. You notice that I was careful to throw in my code, this is a stack allocated object. Whoops, that is not a stack allocated object. I'm sorry. This is a stack allocated object. This is a heap allocated object. It is bad practice to throw a heap allocated object. And the reason is it now places the responsibility for deallocating that object on the shoulders of the programmer. If the programmer forgets to do the deallocation, you get a memory leak. In contrast, if you throw a stack allocated object, then the C runtime environment will ensure that the memory is automatically collected when the catch body that handles that exception finishes. So it is always the case that you should throw a stack allocated object rather than a heap allocated object. And again, the other thing that you want to do is you want to catch them by reference, because that will allow you to modify the object. Also, technically it doesn't create another copy of the object. So it's also more efficient because it's passing by reference as opposed by value. Okay. We talked about that. We've talked about continuation. One thing you need to be careful about with continuation is if you throw out of a, let's say we have main A, B, C, D, and I throw out of D and I only catch in A, the exception in A. So when I throw out of D, C and B are popped off of the stack. And any destructors for stack allocated variables in B and C are executed. The problem is any heap allocated objects in B and C are not deallocated. So you will have a memory leak. So sometimes if you have allocated if you've done heap allocation and your function deallocates those objects before it exits, then you need to place a catch handler in that function in order to do the deallocation, even if normally you wouldn't want to catch the exception. So I've given an example here where main calls f, and f, as you can see, allocates a new int, assigns it 3, calls g, and then deletes x. And you can see what g immediately does is it throws, an exception. So when it throws the exception, you see f doesn't catch it, nor g doesn't handle it, f doesn't handle it, but main does. It catches the exception. So the issue is that since f did not catch the exception, this delete x statement never gets executed, and we have a memory leak. So technically speaking, I should have a catch statement here in f. So I should really put a try. What I should really do is put a try statement around the G, and then a catch of that exception. And I don't need to do a darn thing because now the delete statement is after it. And it will actually, I need to put a delete statement in here because I want to delete X and then I want to rethrow. So I was wrong. I need to put in that catch statement, I put a delete X and then I rethrow to main. I also keep this delete X in after the try block. So I still would have a delete X also after the try block. So all I'm saying is it is fine to skip functions to have the exception be thrown, say, back up to main and allow the intermediate methods to be popped off the stack. But you need to be aware of the fact that while the destructors of stack allocated local variables will be executed, no heap allocated objects will be deallocated, nor will their destructors be called. So that's something dangerous that you have to be aware of when you throw something. Okay. The standard template library provides a exception class which you can include using brackets exception, and it defines a single virtual function called what that allows you to override it and provide some kind of string that describes the exception. So for the exception class, it returns the string standard : exception. Normally, you would override what to provide a more descriptive string description. So what returns a string that describes what exception occurred. And there are several subclasses of exception. Bad alloc is thrown by new. Bad cast if you try to do a dynamic cast and it fails. There are certain runtime errors like underflow and overflow errors. There are some errors thrown by the generics. So out of range is thrown by the vector Q, DQ, and some other collection classes in the standard template library. If you're, for example, out of range with an index, you can also get a length error, which occurs sometimes when resizing is done. So vectors and strings will often try to resize to accommodate bigger, to store more information, but sometimes an error could occur and they would throw a length error. Okay. You can't disable exceptions, so they will get thrown no matter what. You still cannot detect hardware exceptions in C++. So those SIG things like SIGBUS, SIGSEG, they still are handled by that signal method I showed you with C, and you should not be handling them. So these are mostly software errors that you can handle with C++. Okay. Final thing I'm going to talk about today is you need to be very careful when you throw out of a constructor. So in fact, in my example, I threw out of a constructor. Notice here for safe array, I threw out of the constructor. So you need to be careful when you throw out of a constructor. So the issue, let's go back here. So the destructor for that object being constructed will not get called. So if the destructor frees up resources that you allocated in the constructor, then you have to be careful because those resources, if they've already been allocated in the constructor, they need to be deallocated before you throw out of the constructor because the constructor does not get called. Now, the destructor for the member objects will get called. So you don't have to worry about any resources that the stack allocated members may have allocated because their destructors will get called. Okay, and the memory for this object will get freed. And if you are allocating this object off of the heap, which is what I was doing down here when I did my new, right here, my new safe array, I was allocating off the heap. The constructor it threw out of the constructor, but it did return the memory to the heap. So that also occurs. But if I had done any, let's say that for some reason down here, I had done something silly, like before it, I had said data equals new int 10 before I threw out of it. this memory will not be deallocated. If I throw out of the constructor, because the destructor is not executed. So you need to make sure if you throw out of the constructor that any resources you have allocated are returned to the system before you do your throw. Okay, here I had not yet allocated any resources, so it was safe to do this throw. So any questions about this? Okay, I'm going to let you go. I did not get to the Java portion of exception handling, which I can cover fairly quickly on Tuesday. But because I did not get to the Java portion of it, I am not going to make today's quiz due until next Thursday. So I will delay the quiz that was due for that would ordinarily be due on Tuesday for today's lecture. I'm going to push it back until Thursday. You still can complete almost all of the homework. For one thing, Java's exception handling is pretty much identical to C++'s exception handling, and I have just covered all of C++'s exception handling. So on Tuesday, I will quickly go through the ways in which Java's exception handling differs from C++'s exception handling, but the bottom line is not by much, and you should be able to do almost all of homework 5 now based on what I have covered today. So with that, I am going to let you all go. I hope you have a good weekend, and I will see you all come Tuesday.